Okay, so our second video is going to be about the other two types. Actually, for the caliper disc brake and the cone clutch brake, the procedure for the design is going to be similar to those explained for the plate type brakes. The frictional torque is going to be need to be calculated in that case. The other things like the mirror radius and the other stuff also can be calculated the same way. The area is going to be the area of the cone side, which is going to be the area of this side, the contact area, which is not going to be much different. So to calculate the torque, you need to find first the actuation force, and from the actuation force, we can calculate the torque and then continue the same procedure as the one we had earlier. Just to remind you about how the cone type is working. We're going to have the cone-shaped clutch or plate, and it's going to go inside the driving shaft and going to go inside. Well, it's going to be the male and female part, so it's going to be inserted. The contact will be on that face to create the actuation. So the third type is going to be the shoe drum brakes. We start with the short shoe drum brake, and we have the long one, and the design procedure is going to be the same. So take a look to the images that we had for the short drum brake system, and the parameter we have is going to be the workload, W, the length of the lever to create a moment, and this moment will create a normal force on the disc on the side. Okay, this will create a friction force, and this friction force will opposing the rotation, and thus is going to be stopped the disc from rotating. This is actually different types, not much different. It's only about the lever design itself, so we can have a different value for the moment at the point around the point A. So maybe we're going to talk about this one, and we're going to talk about the short shoe first, and then we're going to go for the long shoe. So for the short shoe drum design, we start with the friction force calculation. It's going to be equal to the working force multiplied by the length and divided by the A and divided by the F minus B. Okay, so from that we will find the force. The friction torque in that case is going to be calculated by multiplying by the friction force by the diameter divided by 2 or the radius. Then we got this value. We can calculate the area of the slide. We can continue with the procedure like we done earlier. Find the area, find the absorbed power, and calculate the W over A value. Now, what we call the WR ratio. Now, for the long side, it's not going to be much different once again. It's only about the change in calculating uh, the torques. So for the long short drum brakes, you can see that the contact area between the brake and the disc is going to be longer, and thus the area is going to be higher. The width is going to be also take a consideration to calculate the area. So we start first by calculating the friction torque. Friction torque is going to be the R square multiplied by the coefficient of friction multiplied by W, P maximum multiplied by the cosine of the theta 1 minus the cosine of the theta 2. Now let's see what are these parameters. So the R is going to be the radius of the disk. We can find that from the R we have here. The F is coefficient of friction. W is the width of the disk, the depth of that one. And the P is going to be the maximum force we're going to have on the system, the maximum pressure. And of course, the theta 1 is the maximum contact angle, sorry, the angle between the end of the brake shoe to the pivot point. And theta 1 is from the beginning of the shoe area to the pivot point. So the W itself, the work actuating force, is going to be equal to the Mn plus the Mf divided by L. The Mn is the moment normal of the normal force with respect to the hinge pin, and the Mn usually is going to be calculated as the 0.25, the maximum pressure multiplied by the width radius C value multiplied by 2 theta 1 minus theta 2 minus the sine of the 2 theta 2 plus the sine of 2 theta 1. The MF is going to be the moment of the friction force with respect to the hinge pin, and this will be calculated by the other equation. So the friction power is going to be equal to the torque multiplied by the omega as normal. Now we need to go and calculate the area, divide the power by this area, and we can find the WR ratio or the weight ratio. So the area can be calculated is going to be equal to the LS, or the length of the surface, multiplied by the width. Okay, or this will be equal to 2 multiplied by the width multiplied by the R multiplied by the sine of the theta 1 minus the sine minus theta 1 divided by 2. Okay, so we found the area, we know the power, then we can calculate the weight ratio and compare to the same range that we explained in the first video. So let's have a simple example for that. We have to design a long shoe drum brake to produce a friction torque of 84.75 Newton meters to stop the drum from 12.56 radian per second or 120 RPM. Now we have been given now the torque, and we have been given the omega. So we need to find what will be the parameters of our shoe brake. So the solution will start first by step number 1, select the brake frictional material and specify the desired maximum pressure and the design value for the coefficient of friction. So that's something we're going to design ourselves. We're going to use the standard material to make this brake system. So for this problem, let's choose the molded polymer compounds and design for the approximately 517 kilopascal as a maximum pressure. So the P maximum is going to be 517 kilopascal. Second, propose a trial values for the geometry of the brake drum and the brake pad. Trial value is going to be radius going to be 101.6 millimeters. The C value is going to be 203.2 millimeters. The length is going to be 381 millimeters. The theta 1 is 30 degree and the theta 2 is going to be 150 degree. So now this will help me actually to calculate the width. The width is going to be equal to the torque divided by the R square, the F multiplied by the P maximum multiplied by the cosine of the theta 1 minus cosine of the theta 2. How did we got this equation? Now it's very easy. If we go back, you will find that the torque equation has been rearranged to find the value for the W. Okay, now putting the parameters in, I will get that the width is going to be 36.58 millimeters. Now we're going to round it up this value to be 1.5 inches, or the 38.1 millimeters. Now we know the P maximum now can be calculated. It's going to be 517 multiplied by 10 up to 3 multiplied by 36.58. That's the one we calculated, divided by the 38.1, the value that we had suggested, which is the standard value. So this will drop the maximum pressure to 496.4 kilopascal. That's obvious because the wider, the higher surface area, the lower pressure. Okay. Step number 4 is compute the moment of the normal force on the shoe, or the MN. Now you remember the equation that we suggested earlier. Okay, we have all the parameters. We're going to put them in. So we know the P maximum in kilopascal. We need to change to pascal. We know the value for the W. We know the value for the R. We know the value for the C. Theta 1 and theta 2 are known. So we just put them in this equation, and we will find the MN, or the moment of the normal force. So what you can notice here is that the W that we're using here is going to be the same W that we suggested, not the one that we computed. Okay, it's going to be 0.038, which is 38.1 millimeters. Okay, so by putting this parameter in, and we can calculate that the value for the MN is going to be 577.2 Newton meters. Now, the other moment we would like to find is going to be the friction force moment. And that's the equation we have. Let's check the parameter we need to use. The P maximum is found, W is known, R is known, and cosine or theta 1 and theta 2 and the C are all known. So we put the parameters again, and this will give you that the moment is going to be equal to 84.5 Newton meter. So now we can add those moments, the MF and the MN, and divided by the length, we will find actually what will be the value for the actuation force, or the W. Okay, so this will tell me that the value is going to be equal to 1,241, sorry, 1,294 Newton. Now, the last thing we need to check is going to be, okay, now, will that break is going to be within the requirements? We need to calculate the wear ratio. To calculate the wear ratio, first find the frictional power. This is the torque multiplied by the omega. So it's 1066 watt. Now I just need to find the area and divide the power by the area. So the area, as we mentioned earlier, is 2 multiplied by the width, multiplied by the radius, multiplied by the sine of the theta 1 minus theta 2 divided by 2. And this will give me that the area will be equal to 6,710 millimeters square. Now, just divide the 1,666, 1,066 by this area, and the ratio is going to be 0.159 or 0.16 watt per millimeter square. And this will be as an acceptable ratio, so our design can pass the test. Okay, so the next video is going to be about the banded brakes.